So, yeah, no black holes now. I'm going to be talking about conformal field theories in 4 dimensions with n at least equal to 2 supersymmetry. This is an area where there's been a huge expansion in the landscape of such theories, at least that we're aware of, over, I don't know, over my career in physics. There's a variety of sort of diverse constructions of these things. Conformal gauge theories are the most classical, but they have these class S generalizations. There's a menagerie of Argyres-Douglas type constructions, and then there are more stringy or F-theoretic constructions as well. And the sense one gets is that generically, these sorts of models don't admit conventional microscopic Lagrangian descriptions. And this has motivated a program that some people, including myself, might call the superconformal bootstrap, to try to develop more robust methods to study these kinds of models in a way that doesn't depend on any particular microscopic formulation. And what I'm going to talk about today is sort of an outgrowth of this program. It's really led to a particular powerful new organizational principle for n equals 2 SCFTs in 4 dimensions, which also happens to be a nice, interesting piece of mathematical physics, through a connection to vertex operator algebras, or chiral algebras, for people who don't use the phrase vertex operator algebra. And I'm going to be giving some sort of an overview and update of this program, which has really been ongoing for a while. So the starting point is the algebraic characterization of superconformal field theories, which is via this sort of standard schematic of an OPE. So SCFTs in particular are an OPE algebra of local operators. And in an n equals 2 SCFT in 4 dimensions, these local operators organize into representations of the SU2, 2/2 superconformal algebra, and in particular into representations of the SO1, 3 Lorentz group, scaling U1R and SU2R symmetries. And the way that we find a story about vertex algebras is by carving out some sort of algebraic substructure of the full OPE algebra by passing to the cohomology of a carefully chosen supercharge, like one does with classic constructions like chiral rings, except in this case we're using this funny supercharge, which is a combination of a Poincare supercharge, usually called Q, and some superconformal supercharge called S. And if you make this careful choice, then you find that in the cohomology of that supercharge, the local operators that survive passage to cohomology are restricted to lie on a particular complex plane, which I'll take to be parameterized by coordinates z and z bar inside of the C2 spacetime. And the OPE of those local operators at the level of Q cohomology acquires a meromorphic dependence on this coordinate z instead of a general dependence on z and z bar. And this essentially guarantees that the structure that I'm getting at the end of the day, the OPE, the algebraic structure on these cohomology classes, has the structure of a vertex operator algebra or chiral algebra. And so we can formalize this by some map that I usually denote by a double barrel V from 4-dimensional n equals 2 SCFTs T to an associated vertex operator algebra. In slightly more detail, the way that this works is that the local operators that survive in the Q cohomology are in one-to-one correspondence with things called Schur operators, named that because they contribute to a certain limit of the superconformal index called the Schur limit. These are operators that obey a couple of linear relations on their quantum numbers. And for reference, these Schur operators include some sort of favorites of people who work with n equals 2 SCFTs, which are Higgs branch chiral ring operators, but those are not the generic thing. The generic thing living in this Q cohomology are some sort of semi-short operators obeying sort of unusual shortening conditions that live in multiplets called C-hat multiplets, if you know the classification of n equals 2 superconformal representations by Dolan and Osborne. There's a conspicuous absence of the Coulomb branch chiral ring operators, which are one of the other favorites in the world of 4D n equals 2. And by construction, we can say quite a bit about the chiral algebras that come out of this construction. So there's some local operators that have sort of universal images after you pass to Q cohomology. So if I have a stress tensor in 4 dimensions, T mu nu, then that thing lives in a supermultiplet that includes the SU2R current, which has a particular component, which is a Schur operator, who at the level of Q cohomology deserves to be called T of Z, because that thing, by virtue of superconformal ward identity, generates a Virasoro subalgebra of this vertex operator algebra that you're getting on general grounds. And interestingly, the central charge of that Virasoro algebra is related to the C central charge of your four-dimensional theory by a factor of -12. So in a unitary four-dimensional theory, you get non-unitary Virasoro symmetry. Similarly, if I have global G symmetry in 4 dimensions, then that thing has an attendant conserved current called J mu, and that thing lives in a supermultiplet with a Higgs-Chiral ring operator, usually called mu A, which is the so-called moment map of the Higgs-Chiral ring. That thing is a sure operator, and at the level of Q cohomology, it deserves to be called JA of Z, because by virtue of word identities, it generates G hat, affine Kac-Moody subalgebra of the full associated VOA. Again, the level of that Kac-Moody algebra is related to the so-called flavor central charge K4D of the 4D theory by a factor, which is -1/2, and K4D is positive in unitary four-dimensional theories, so we're getting negative level affine Kac-Moody subalgebras. Some more general properties that you can see sort of structurally is that the generators of the Higgs branch chiral ring of your 4D theory necessarily give rise to strong generators of the vertex operator algebra. This means that these are operators that can't be written as normally ordered products of any other operators. Sort of by construction, the sure limit of the superconformal index is just the same thing as the vacuum character of this vertex algebra. And somewhat importantly, the VOA is independent of any marginal couplings by an honor normalization theorem. So this is some algebraic structure which is sort of an invariant on the conformal manifold of your four-dimensional theory. Okay, so those were sort of generalities. What do we actually find in examples, just for people who haven't seen these things before? There's now quite a large catalog of actual 4D SCFTs where we know what the associated VOA is via various arguments. So free hypermultiplet just turns out to be a dimension 1/2 beta gamma system, also called a symplectic boson. But then if you start studying sort of interesting theories, like there's a family of Algebras-Douglas SCFTs called the A1 A2N or A1 A even Algebras-Douglas SCFTs. And these things give you Virasoro VOAs on the nose, but at interesting values of the central charge, in particular the values associated to the 2, odd non-unitary minimal models. More generally, if you study another class of Algebras-Douglas SCFTs, the so-called A1 D odd Algebras-Douglas SCFTs, then you get pure affine Kac-Moody VOAs, but again at interesting values of their parameters. So this is at level -4n over 2n plus 1, so these are negative fractional levels. These turn out to be what are called Katz-Wakimoto admissible levels, so these are known interesting levels to find affine Kac-Moody algebras at. And because it's going to reappear later, I mentioned that the so-called rank 1 F-theory SCFTs, so these are the theories that you get if you take a single D3 brane and put it at a singular fiber of a K3 compactification of F-theory. Then you get, again, pure affine Kac-Moody associated to type G, where G labels the type of singularity in F-theory, living in one of these, the algebras, at a level which is -1 minus the dual Coxeter number of the associated G over 6. Those are a number of interesting examples, but they're in some sense misleading because these were all what you might call linear vertex operator algebras. But the general case is that you actually find nonlinear vertex operator algebras that some people call W algebras. So for example, if you consider NF equals 2NC superconformal QCD, then the baryonic generators of the Higgs chiral ring give rise to nonlinear W currents of conformal spin NC over 2. So for SU3 and bigger, these are some nonlinear W currents. So the sorts of things that you're getting out of this construction is everything from rational Virasoro vertex algebras that we know and love to sort of weird irrational W algebras. Now, there's an immediate interesting part of this story, which is that the VOAs that I'm talking about are specified by some finite amount of data in the textbooks. You go and you read that in order to talk about the Virasoro algebra, you write down the singular OPE of T of Z with T of W, and then you're done. So these things are specified by a finite amount of data, which is the singular OPEs of the strong generators of the vertex algebra, but they encode an infinite number of 2- and 3-point functions of the vertex algebra, and by virtue of the fact that this vertex algebra is sort of living inside of a 4-dimensional n equals 2 SCFT, it's encoding somehow an infinite number of 4-dimensional 2- and 3-point functions. But obviously, these vertex algebras are not manifestly unitary. I just said that you get negative values of C and negative values of K, sort of hallmarks of non-unitary CFTs. So it's not at all obvious that the 2- and 3-point functions in 4 dimensions that you read out of this structure are going to obey any good rules associated with unitarity in 4 dimensions. And this gives you real restrictions on the vertex algebras that can arise. The simplest, dumbest example being that I just told you that C and K have to be negative. But this is really the tip of an interesting iceberg. So suppose I have a four-dimensional theory that has GF global symmetry. Then I said that the moment map operator in the Higgs-Cairo ring of that theory gives rise to an affine current JA. And then I can consider the normally ordered product of JA with JB, sort of quadratic composites of the affine currents. And if you look into sort of the way that this thing is built out of four-dimensional things, then you see that this normally ordered product of affine currents, when interpreted in four-dimensional terms, has to be some sort of admixture of the operator associated to the Higgs branch Cairo ring product of mu A with mu B, and also the two-dimensional stress tensor. So this is some weird admixture of operators that live in different superconformal representations. In particular, the stress tensor is a G singlet. So if I project this thing onto non-G singlet representations, then I'm going to get things that can be purely interpreted as Higgs branch operators in four dimensions. But in the singlet channel, I get some admixture. And if I want to get something which is pure Higgs branch, I'm going to have to orthogonalize with respect to the stress tensor. And then once I've done this, the VOA norms of these states, so the VOA knows everything about how to compute correlation functions. So the norms of these states are fixed algebraically in terms of K and C. But four-dimensional unitarity dictates that the norms in the VOA of these mu squared type operators have to be positive. And this leads to some non-trivial unitarity bounds. So for example, you find out that the Kac-Moody level K, the Virasoro central charge C, and the dimension and dual Coxeter number of the group G have to obey this relation, which after massaging tells you that if the Kac-Moody level is greater than minus the dual Coxeter number, the so-called critical level, then the central charge is bounded below by the Sugawara value of the central charge. So this is the Virasoro central charge getting a lower bound, so that's an upper bound on the four-dimensional central charge because they're related by a minus sign. Similarly, all of these non-G singlet representations give me absolute upper bounds on the Kac-Moody levels for a given choice of group, which turn into lower bounds for the flavor central charges in four dimensions. You can push a little bit further, and somewhat surprisingly, it's a non-trivial generalization when you consider flavor symmetry which is reductive but not simple. So consider a flavor symmetry which is some combination of simple and U1 factors. And now, again, focus on these sort of quadratic composites of affine currents that are singlets under GF. So these are the sort of Sugawara type vectors that you construct out of affine currents. And again, you can massage this thing so that you end up looking at operators in the vertex algebra that are definitely related to specific four-dimensional supermultiplets, in particular these Higgs branch operators. And you can compute a matrix of two-point functions of those Higgs branch operators entirely in terms of vertex algebra data. You get some slightly complicated non-diagonal matrix because once you orthogonalize these things with respect to the Virasoro stress tensor, you get some mixing. And it's now a somewhat complicated, delicate set of constraints that you get by demanding that this matrix be positive semi-definite that I summarize on this page. So in order to summarize it, I need to define some terminology. If a Kac-Moody level is greater than the critical level, then it is called subcritical. If it's equal, then it's called critical. If it's less, it's called supercritical. That might sound counterintuitive, but if you switch to four-dimensional language, it makes sense. And then you end up with this sort of complicated set of rules that says that if you have any two simple factors in your flavor symmetry, which are at the critical level, then you get a Higgs branch Cairo ring relation that sets trace mu squared for one flavor factor equal to trace mu squared in the other flavor factor. If you have at least one critical factor, then you can have no subcritical factors. If you have any subcritical factors, then you get a lower bound on the Virasoro central charge, so an upper bound on the four-dimensional C central charge. And there can be at most one subcritical factor. So this is a sort of complicated set of constraints, which is just automatically coming out of this non-trivial compatibility of sort of the algebra of the VOA with the rules of unitarity in four dimensions. So this is summarizing what I just said. There's some non-trivial sort of interplay between the algebraic structure of VOAs and unitarity, but in the story I just told, it was important that I be able to unambiguously identify operators in the VOA with operators that lived in specific supermultiplets in four dimensions, and I sort of obliquely said that I could do this. But it's actually difficult to push this story of unitarity bounds further, precisely because it's hard to find a dictionary in general between VOA states and operators with definite four-dimensional quantum numbers. This problem arises in some sense because the space of Schur operators that constitutes the vertex operator algebra is triply graded. It's graded by H, which you can think of as the sort of VOA conformal dimension, U1 R charge, and also SU2 R charge. These are all good quantum numbers for the set of Schur operators. But once you define this VOA structure on this vector space, you don't see SU2 R charge anymore. You only have a bigrading by H and lowercase r, and capital R is not conserved by the OPE. It's violated downwards, so there's some filtration instead of a grading that's allowed at some technical point. But you don't see all of the sort of graded vector space structure on this vertex algebra that's in principle there for four-dimensional reasons. And this makes it hard to see four-dimensional physics in general, starting with a VOA. So there's a question that's sort of a general question that one should want to answer, which is given a vertex algebra that's associated with some 4D theory, how much four-dimensional physics can I actually recover? So a simple version of this question is, can I recover the Higgs branch, which is some sort of basic invariant of a 4D n equals 2 SCFT if I'm given the vertex algebra? And the answer to this is apparently yes, but it's non-trivially yes. So it turns out that there's a canonical construction in the vertex algebra literature of a finite-dimensional Poisson variety that you can associate to any vertex algebra. It's called the associated variety. There's some technical definition. There's some big subspace of a vertex algebra, which is all of the operators that you can build involving derivatives. So you take all of your operators and take normal ordered products of them. If you ever sprinkle in a derivative, you put that in this space called C2 of V, and then you quotient by it. So you're trying to sort of quotient out by derivatives to get something with no derivatives left. And then you have to technically further quotient by nilpotent things, which is what this lowercase m means. But then you get a finitely generated commutative C algebra, which you can think of as defining an algebraic variety. That's the associated variety of a vertex algebra. And we've conjectured and checked in an infinity of cases that for vertex algebras arising from four-dimensional SCFTs, the associated variety is the same thing as the Higgs branch of vacua. But this is a non-trivial statement. It requires some technical condition on this R filtration that I mentioned before, and a proof is not yet forthcoming, but this seems to be a general principle. So there's sort of a little bit of geometric structure that you can extract from this vertex algebra that you care about, but it's a non-trivial fact that you can do it. In particular, a consequence of this conjecture is that the associated variety of these vertex algebras is symplectic. The Higgs branch of a 4D n equals 2 theory is a symplectic variety. In contrast, a generic vertex algebra has a Poisson but not symplectic associated variety. So here's some examples. If you take the Virasoro algebra at generic values of the central charge, then its associated variety is just C with the trivial Poisson bracket. So that's Poisson but not symplectic. On the other hand, if you specialize the central charge to one of the minimal model values of the central charge, then the associated variety becomes a point, and a point is a trivial example of a symplectic variety, sort of a degenerate example. If you go to affine Kac-Moody VOAs, then again, if you consider the generic values of K, then the associated variety is just the complexified Lie algebra, which is again Poisson, but not symplectic. If you specialize to the integrable levels, so natural numbers for the level, which are familiar from rational conformal field theory, then again you get a point, which is again symplectic, strictly speaking. But now there's other interesting values of the level, so negative rational levels of the form minus the dual Coxeter number plus P over Q have associated variety, which is the closure of a nilpotent orbit inside of the complexified Lie algebra, and these things are known to be symplectic. So if you haven't seen any of this stuff before, you can think of this statement as being that the symplectic condition for associated varieties is some sort of relaxing of the condition on rational vertex algebras that the associated variety be trivial, be just a point. So in this case corresponding to rational VOAs, the associated variety was just trivial, and in that case the VOA is called C2 cofinite, and we're finding some sort of relaxing of that condition, which is still some sort of partial finiteness condition associated to symplecticness of the associated variety. Tomoyuki Arakawa and Kazuya Kawasetsu have studied this class of vertex algebras, and for historical reasons, they called them quasi-Lie vertex operator algebras. And their work is relevant for many reasons, but in particular, they proved a theorem that the vacuum character of any quasi-least vertex operator algebra solves a linear modular differential equation of weight 0, which translated means that the Schur superconformal index, which is the same thing as the vacuum character by the previous discussion, is always the solution of such a differential equation, and so in particular is a component of a finite dimensional vector-valued modular form, really a vector-valued quasi-modular form. So here we see that sort of the abstract structure of vertex algebras immediately puts out a pretty complicated structure and surprising structure for some related observable, the superconformal index. And so for this class of rank 1 F-theory SCFTs that I mentioned before, just to flash an equation, in those cases the associated variety is the minimal nilpotent orbit of the relevant Lie algebra G, and then you can just go and check, and you find that the Schur index for all of those SCFTs is the solution of a second-order modular differential equation that can be written down in this extremely uniform way, where it depends only on the dual Coxeter number of the associated G. And this sort of modularity of the Schur index is some sort of generalization of results that were previously seen by Drucker and Razamat for the Schur index of n equals 2 and n equals 4 theories. Okay, so I should speed up a little bit. The story I was just telling was about trying to extract some nice geometric structure from the vertex algebra. I said it was non-trivially possible to do it. There was some map that took a vertex algebra associated to a 4D theory and gave me back the Higgs branch. What we've been discovering more recently is that there's actually perhaps a closer connection to Higgs branch physics than just what's implied by that map, which is a map in the other direction, which is that we seem to be able to take the Higgs branch physics of a 4D n equals 2 SCFT and recover the associated vertex algebra via a free field realization. And we're finding very economical free field realizations of these vertex algebras, economical in the sense that they use fewer free fields than you might have thought. So in general, we have constructions using a lattice VOA of signature D comma D, where D is the quaternionic dimension of the Higgs branch. And if you compare this to sort of generic cases, if you look at something like the Wakimoto realization of an Affine-Katz-Moody VOA, then you need dim G many chiral bosons, whereas for these F-theory SCFTs, you need a 1-1 lattice and H check -2 symplectic bosons. So if you plug in E8, this means that we're getting by with 58 instead of 248 chiral bosons as sort of the ingredient. So there's some economy in these constructions associated with the fact that we're looking at these vertex algebras at special values of the level, where their associated variety is symplectic, and this is all tied up with some good properties of 4-dimensional SCFTs. Okay, so then just to say this in slightly more detail, still very fast, the idea is that if we specify the Higgs branch physics of a theory, which I take to mean specifying the Higgs branch as a holomorphic symplectic variety, and also perhaps specifying if there's some non-trivial low-energy effective field theory still living at a generic point on the Higgs branch, some residual degrees of freedom, then from this we seem to be able to concoct these sorts of economical or minimal free field realizations of these VOAs, although in practice this is not quite systematic yet and requires some artistry. So as an example, if you look at the A1D3 Argyros-Douglas theory, whose Higgs branch is C2 mod Z2, which is also the variety defined by xy plus z squared equals 0 in C3, then the way the game looks is that you look at a big open subset of this algebraic variety. So I look at the subset where x is not equal to 0, and that thing looks like the cotangent bundle of C star. And then we associate this 1,1 signature lattice VOA with the cotangent bundle of C star. This is, in some sense, you should think of it as an affinization of T star of C star. And then using this sort of finite dimensional geometric analog, you can promote the coordinates x and z that parameterize T star, C star to an exponentiated chiral boson. So x is the coordinate on C star, so it's invertible. So you should think of an exponentiated chiral boson as being sort of an invertible free field in a vertex algebra. And z, which lives in the fiber, so it's not invertible, looks like some combination of U1s. And then it turns out that you can take this sort of finite dimensional model and upgrade it and fix things up to quantum corrections in order to reproduce a free field construction of the vertex algebra associated to this theory. That was very fast, but I have 10 seconds left. So what we've actually found, that's example 0 in what turns out to be a very broad story. So we have many more examples, and each one is sort of a beautiful gem on its own. It's always surprising when these free field realizations work using a very small number of free fields. So we can build the rank 2 F-theory SCFTs, n equals 4 super Yang-Mills series, linear conformal quivers, a lot of class S constructions. These things all seem to work the same way. And I'll put up the parting thoughts and stop talking.
Thank you very much. Other questions? This one back there.
So we know that the Higgs branch of a n equals 2 SCFT is hyperkähler and has scaling symmetry and things like that. Does the relation to VOAs impose any new constraints on the geometry of Higgs branches?
Yeah. The answer is yes, although I think that the answer is probably an even stronger yes than I can really make clear. So if you go back to these unitarity constraints, then you can actually, then we actually showed back in 2013, that, for example, if you want to imagine that your four-dimensional theory has a Higgs branch which is a minimal nilpotent orbit, then you can only get this series of SU2, SU3, D4, E6, E7, E8, and also F4 or G2 as the Lie algebra. And otherwise, there's an incompatibility with unitarity. So you can't satisfy all of the right unitarity bounds. I suspect that there's, so my fantasy that lives on this slide that I didn't read off is that there's going to be sort of a more systematic story of trying to build up VOAs associated to Higgs branches along with decorations and trying to simultaneously impose unitarity. And it seems like this is a sort of non-trivially constrained problem, but it's not systematic yet.
Other questions? All right. So let's thank Chris again.